So it is my pleasure to introduce Dan Karig. I won't embarrass him with the great picture that I dug up of him in his youth. But I was just saying to him that there's no reason to be embarrassed about this picture because it shows him a very buff-looking geologist, but he's on the Glomar Challenger. And I just wanted to say that Dan was known initially in his career as a structural geologist, a tectonicist, worked on island arcs at a very exciting time during the invention of plate tectonics. After getting his PhD at Scripps, he hung out at Scripps for a little while, went to the University of California, Santa Barbara, and then came here to Cornell in 1973, and he's been here ever since as a tectonicist. And he dabbled in a few other things, but here he is on the Glomar Challenger in the heady days of the deep sea drilling project, and I think that says something about his breadth of interests. Which brings us to why he's here today. He retired from Cornell in 1998. I met him actually because he was chair of the department when I arrived in Ithaca, and one of his duties was transferring the remainder of the Cornell fossil collection to PRI. He retired and then took on something completely different, and he's become an expert in the glacial geology of the Cayuga Basin, and that's what he's going to talk to us about today. So no further ado, Dr. Karig.
I don't know about expert, but okay. When I was in the Army, they told me the way to give a good talk is you tell them what you're going to tell them, and then you tell them, and then you tell them what you told them. But I'm not going to do that today. I'm going to present this sort of like a detective story, and I'm not going to tell you anything all about the outrageous model until the very end. But I'm going to sort of bring you along, showing you the evidence of the field data as I got it. Pretty close anyway. Okay, but let me also start by talking a little bit about something that I'm not going to talk any more about. It's the general glacial background around here. Okay, I shouldn't have put that on right away. But the Earth started turning cold probably 30 million years ago, but that was in Antarctica. And it wasn't until about, 5 million years ago that the Arctic started getting cold. And about 1 million or so years ago, ice first started coming down here to Ithaca. I mean, we don't know that from what we see here, but in America, in the United States anyway. And since that time, we don't know how many times ice has covered Ithaca, but it's probably been on the order of a dozen, not 100. And it's kind of interesting, now that we get to this slide here, that the glaciation occurs in cycles. And these cycles are roughly about 100,000 years, I won't get why. But, you don't have a glacial period, real cold, then all of a sudden it gets real warm and stays warm for a while and then gets cold again. What you have instead are these very asymmetric cycles that they start, well, let's start at this is the warm end and this is the cold end down here. One cycle would say it starts by getting very, very warm, very rapidly, and then cools down very irregularly. Actually, I should go with this one here, this last cycle, because it almost shows it the best. This is one we'll talk a little more. Up and down, up and down, up and down, getting colder and colder and colder. And usually the very coldest part is just before it gets very warm again. And, so these interglacials, these warm periods, usually the warmest part is right after it warms up. And it doesn't stay that warm. You see it, well, you can see. And this is actually carbon dioxide, but temperature looks exactly the same. Okay, so today we're going to be talking about the last of these cycles, the Wisconsin. And I'm actually going to be only talking about a little part of this warm up here, the deglaciation part. But it's just sort of, we have evidence for older stuff here in Ithaca. The oldest obvious, pure evidence in sediments is here in this warm part, so-called Sangamon interglacial. We have sediments along, well, it's not very far, it's down the hill there of that age. And we also have some interglacial gorges that were probably formed in that area. We don't have any sediments, but this Illinois glacial period was probably the big mover, the thing that, probably the glacial cycle that did the heavy lifting, or did a lot of the gorge or trough digging. Because the Wisconsin, amazingly, even though it's just as cold, doesn't seem to have done as much massive gouging. Okay, we don't have any of these cycles here represented, but we do seem to have found some glacial sediments that represent this middle Wisconsin period right in here. And that was, I mean, I've been working on it, just got a paper published on it, but this is due to a find in 1939 by a graduate student named Vic Schmidt, who did his PhD there, and I just got sent this picture from his son-in-law. He found these barbs. They're just above the city foot dam, the city reservoir, in this thing called the high bank. And that's the picture of the high bank there. And Vic was an amazing digger. I mean, he dug pit. Wow! He dug. You know, all these pits here, and these pits have all these bars, and I won't go into it, but bars are annual deposits of clay in proglacial lakes that represent freezing and thawing kind of thing. They're really spectacular things. You get up there red and blue almost. And he developed a tool that actually would collect a core, a square-like core of these bars. And he basically spent the rest of his life on and off working in this area and collected an immense amount of data. The barbs are the most spectacular. There's actually a sample of that in the glacial collection. And when Vic died, he left all this stuff to PRI. And somebody at PRI named Allman asked if I'd curate or edit that stuff because I had been working there, and I'm still doing it. I hope I don't leave half as much stuff behind as he did. Okay, so onward to, let me go back to use this here. Again, we're going to talk about just this deglaciation period here. Now, at the peak of glaciation here, about 25,000 years ago, ice went all the way down into Pennsylvania. And ice was here, ice thickness here was on the order of probably in excess of a mile. I mean, I've been to Greenland, I've been to ice in all these places, and it just, I've seen all this ice, but it's just still hard to believe we had a mile of ice above us here. Okay, and then the ice started retreating as it warmed up here. And we're not exactly sure how that happened. Everybody will agree that it retreated and then re-advanced and then retreated some more. But it's arguable whether it retreated all the way back into the Ontario Basin and then advanced, or whether, as I think, it only got back to south of Ithaca a little ways and up to Ithaca and then advanced again. But that little advance is sort of the last major advance that we had that affected Ithaca, and we call it the valley heads. It left a number of features that we see today. Matter of fact, the ornamentation of the glaciation around here was all formed during this last little advance and the retreat from it. For instance, all the kettles and caves around here were formed then, and the gorges were formed after that. And okay, let me wait till I get the rest of it. It also left these things called the valley heads moraines, which are huge piles of gravel and sand and everything, just about at the watershed between the Susquehanna and the Great Lakes. Actually, the glacier helped form or locate that watershed. Okay, the model that has been around, and I'll tell you about in a minute, was devised or concocted or generated by a fellow named Ralph Stockton Tarr, one of the first geomorphologists here. He's an absolutely amazing guy. He was into this game at the end of the 19th century, late 1800s, early 1900s. And at this time, they knew glaciers had come here, but they didn't know much about them at all. They didn't know how much they eroded. They didn't know what kind of features. They didn't know how glaciers worked. And remember, they didn't have motor vehicles to speak of then. He went first to Greenland, and then he went several times to Alaska to find out for himself what glaciers really did. I mean, you don't just book a trip at that time. It was really something. And not only that, but he mapped a tremendous area here. 1 to 62,500 quadrangles. I forget the names of them, but it covered all Ithaca and all the way over Watkins Glen to the south. I mean, just an amazing amount of mapping. And I took a photograph of this map. This is part of his map. This is a work map that we had at Cornell. And just to show you where we are, Ithaca is right up there. Ithaca College is there. There's 6 Mile Creek along there. There's Eastmerd, Slaterville, Brookendale. Okay, but there's no map out now that's anywhere near as detailed as that. I'll show you the final version of this later, but I think this is amazing too. The guy was everywhere, and he didn't live that long. He's a hemophiliac and died at a very young age. Okay, so what was his model? Okay, this is from the book by one of the students, Von Engel. Otto Von Engel was one of the students. And the model is that, okay, at the peak of the valley heads advanced, or Fort Bruce advanced, the glacier, well, you can see, Ithaca's back up in here somewhere. There's Caroline's. This is roughly the same all the way across. The ice went all the way down to the watershed between Susquehanna and the Great Lakes and drained south. All the water then came out of the glacier. Okay. Here's the guts of the model. As the ice started retreating, because the watershed was shallower than the front of the ice, lakes got trapped in front of all these little glacial tongues. And the lakes overflowed at the lowest point of the watershed in here. Okay, and as the ice retreated back along here, the lakes increased in size, and finally, like right in here, when the ice retreated past this nose here, this lake was higher in elevation than this lake, and so this lake drained down to the elevation of this lake here. And okay, and this lake is called Lake Ithaca. Everybody learns about Lake Ithaca. The Lake Ithaca drained south through this area here just north of Wilseyville at an elevation of 980 feet, because that's what you see there now is the minimum elevation in that, or maximum elevation you go off. But anyway, that's where the water came out. And so Lake Ithaca stayed at 980 feet for a reasonably long time, at least hundreds of years. I don't know how much longer than that. Okay. One thing to give you a little time frame. These guys didn't have any idea of time, but we don't have any dates here. But from out west, the time that this ice was at its local maximum was about 16,500 years ago. We have some more dates. When Lake Ithaca when the present Lake Cayuga reached its form, to get at its present level, was about 14,000 years ago. And so you only have, well, maybe 13 and a half. But anyway, you've got 3,000 years to do all the sorts of things that I'm going to talk about today and deglaciate this area. Things had to happen pretty fast. Okay. I mean, to me, this is a logical model, and I believed it, and I passed it on to students, and it's based on two basic assumptions. One of them is that ice is impermeable and acts as a dam, and the other assumption is that you look at the topography, and you can pick out where these lakes should overflow. So all you have to do is look at a topo map or analyze a topo map, and you can get this, you can develop this chain of lakes, temporal chain of lakes, because as the ice retreated further, it found a way around by Interlaken, drained the area from Seneca. They call that a new lake, and there's a whole series of these lakes. Every time the lake hit a new outlet, they gave it a new name. So anyway, as Warren said, I used to be worked in island arts and stuff. When I retired, I couldn't do that anymore. It cost too much money running ships, and so I decided to learn something about the local glacial geology, because I live in 6 Mile Creek, just about right in there somewhere. So I started my sort of looking, we have 40 acres, so I started looking at what was in my backyard and expanded that by going up and down the stream here. And then at the same time, he became a friend of mine, Todd Miller from the U.S. Geological Survey, who was studying this area here as an aquifer study. He's a hydrogeologist. So I went down and sort of worked with him and learned about this area, and then I got involved and started looking here, and then I started looking up in here. And then I did this in more detail. In these areas was just looking at critical outcrops. And since then I've been working in the Cayuga Trough, doing some coring and bogs here. We had a well drilled in here, and this is last year. I messed around in Fall Creek I'm not mapping there, I'm just looking for problem solving in a way. But I guess that's an excuse, or not an excuse, a defense to say that I have been trying to look at the larger picture. Okay, so the first thing I did, well, every day when I drove home from work along Sedimentation Road, I noticed that, that there were terraces down towards 6 Mile Creek. This is a work geologic map. You're going to see this a number of times, so I don't explain everything now, but there's 6 Mile Creek. Brookendale's right there, Ithaca's right there. I'm sure you all know where you are here. And I'm right here. And here are these terraces on both sides. They don't end like that. They smoothly go up the wall, but up the slope of the valley. But it's pretty obvious that these terraces were once one great big surface. They've been cut up into pieces by erosion along 6 Mile and its tributaries. And these contours here are on that surface. And it defines a beautiful, smooth, sort of, well, look at one dimension, a bowl-shaped feature. And what people assumed that was is the floor of this Lake Ithaca. And there were no, I'll show you when we get down here, there were no kettles and cames, if you know what they are. There are almost no features on top of this smooth surface here, except for these guys. And Tar call those deltas. They're sort of fan-like deposits of gravel, and they actually extend out further here. They call those deltas as well. We'll talk about those some more. So, I go up this little gully here to look at what's under those terraces, and this is what it looks like. It's a blue-gray, silty clay, sort of massive. Sometimes you think you can see some bedding here and there, but most of the time it's just pure massive blue-gray clay. So, I didn't think much about it. It's sort of like what we cored in Cayuga Lake. And I go down to the creek behind our house, and you see this stuff here, which is classic till. Blue-gray clay as a matrix, and then these angular boulders, some of them pretty big, good size and everything. And so, I thought, okay, there's till underneath and there's sort of lake sediments up above. Then I started wandering around, and we're looking in all the little tribs, and up under some of the terraces I should say, sometimes you find a rock or two in here, and you figure, well, that's just what we call drop stones. They fell out of the ice, and icebergs floating around. But there's too many of these class in here to be drop stones, and they're not organized like drop stones or anything. And other places down in the creek, actually right along the same stream bank, after more stream erosion, you see these highly deformed, obviously lake sediments, and they're amazing. Now, Anyway, long story short, I came to another aspect of it too, that when I started getting suspicious, I took samples of this stuff and measured bulk density and porosity, and they're way too dense and not nearly as porous as postglacial lake sediments ought to be. They were subjected to high consolidation stresses. Anyway, so I came to the conclusion, these aren't lake sediments, this is till. And I couldn't find any lake sediments on the surface at all. So why not? Well, I don't see you in here. Art Bloom said, well, that's because the lake wasn't there long enough and the sediments weren't that thick, and during agricultural times, you know, they eroded away and this kind of stuff. But these proglacial lakes, if you go to them and take measurements, the sedimentation rate's like an inch a year. I mean, they're terribly turbid. Stuff's coming out of the water like crazy. And even, you know, a few hundred years, it's going to give you a fair thickness of sediment. So I thought, okay, what I'll do is I'll go up that little gully and I'll dig a hole, try to get through that gravel layer and see if there's any, if it was a delta, there should be some lake sediments protected underneath it. So I go up the gully and I dig a hole. And I put this in here for two reasons. First of all, doing quaternary geology is kind of, it's different, let's put it that way. The exposures come and go. When a flood comes along, like that one it was 2010 or something, man, you find all sorts of things exposed. It's really wonderful. A year later, you can hardly see a thing. It's just, they're totally destroyed. And by and large, the only way that you can get good samples or good evidence is dig holes. And you've got to dig them through the soil. That's a mattock there, and these trees are about a foot thick, so that's about a 6 foot deep hole. This is bigger than I usually had to dig, because you have to dig through the soil, you got to dig through the roots, and you got to dig through the altered part of the material to get down to fresh stuff. And so there's a lot of work involved. Okay, so anyway, let's look at the bottom of that hole. That's my wallet for scale. And the colors are weird, because I had to take a flash in here. This is till, and it's brown, because as you'll see later, that's the color that blue-gray stuff turns when it's oxidized in weather. And there's no lake sediments whatsoever here. This stuff, there's cobbles through here. It's kind of weird. It's not terribly organized. It doesn't look like delta at all. I mean, it's some sort of like mass deposit. You look at analyze the pebbles, and they're all local bedrock. So this stuff came from the local hills. It's what we call inwash, one way or the other. It either came on top of the ice and the ice melted and it fell down, or it just slumped in. But anyway, there's no lake sediments. So that's, what's going on? So then I went downstream into the gorge area. Again, there's the 30-foot dam, and there's the wildflower area in here. And I saw, same till and same stuff as I saw up there, except that on top of the till, these green globs, that it was obvious layered, bedded post-glacial sediment. And, at the base, it was, where I found it, it's real fine-grained sand, sometimes even silt, and it gets, these things get about 50 feet thick in places, and that one's even more. And they're flat top, although the tops are tilted, I mean, it's plainer. And towards the top, there's gravel and cobbles and stuff like that. So, this is sort of proglacial lake. And there are no good exposures. I couldn't dig any pits, but here's I tried to get the best focus. This is a little tiny photograph from a thesis by a guy named Filmer, about 1910. Down by the water plant, by Van Atta's Dam, or Giles Street, there used to be a quarry there, and that quarry showed this section really well, and they described it as very thin-bedded lake clays at the bottom, overlaid by deltaic material. And I think this is the deltaic material here, and you start seeing layering stuff here. I don't know what's down below. I tried like crazy to find some of this thin-bedded lake stuff because I really want to know how old it was. Never could. I kept coring, and I'd only get real fine sand and silt right above till. But it definitely, that's a proglacial lake deposit. But the top of it's only 800 feet above sea level. It's not 980 like that top also. It's a delta, and deltas are right sort of at lake level. So that sort of marks the top, what the lake should have been. But there's something even weirder about this sequence. Most proglacial lakes, the sediment sequence that's deposited, and this is classic, there's some models of this stuff. It starts out with really coarse-grained stuff because right at the front of the glacier, the glacier is pushing out all sorts of garbage, subglacial fans and stuff falling off the ice itself and everything. So the bottom layer should be really, really coarse. And then as the ice moves away, the stuff that's deposited should be the fine-grained lake sediments. And then if the lake actually fills up, then you get this coarse-grained stuff at the top. But there was no coarse-grained stuff at the bottom at all. I don't know how many holes I dug, cores I made, but it's always real fine-grained stuff at the bottom. So another problem. So went the other direction, and upstream. Actually, I went up to visit Todd. He was drilling in this area here. This is a delta. I mean, it's a real delta. Nobody can get fooled by this. This is where the University of Sand and Gravel is. Brookendale's right there. You've probably seen that mess there.
Those are pissing all over driveways.
Yeah, right. It's on our driveway too. But it was fed from upstream. There's no doubt about that. We'll talk about it a little later. But anyway, here's a picture of the high bank there at that quarry, and shows what we call foreset beds. We're looking east into the wall there. It's about a 50-foot wall. And you're looking right into the delta, and actually these sediments are tilted towards you here, but you can't see that tilt. But you can see there's one bunch of these things all belong together, sort of with a convex upward top. That means that the feeder was somewhere in this area. Here's another set. You can see that it's tilted this way here. They formed another convex upward array, but 6 Mile Creek is eroded away, formed since then. This is older than 6 Mile Creek. So it's fine, except that Todd was drilling off to the left here, over to the south. And, okay, there's Todd. And we're looking at the same material, but now we're looking sort of northwest into it. And these are foresets again. They're actually dipping steeper because they're dipping away from you. And there's some up above as well. But look at this devil. You know what that is? That's till. There's the blue-gray stuff in the middle. It has rocks in it and glass in it. And there's the oxidized margins. I mean, I've shown this to a lot of geologists. There's no doubt about it. It's till. Well, what does that mean? That means that that delta didn't go into some big lake. Especially it didn't go into Lake Ithaca. It went into a little lake that was right next to the ice, and every once in a while the ice would actually close the lake up. And the ice, that was laid down by ice. And the more I mapped around this area, I found till up above the delta, above it. Art Boom found some up there as well. And also, interbedded with it. The long and short of it is that the lake that this delta went into, and I should mention this, Von Engel thought that delta actually had something to do with Lake Ithaca. Well, it doesn't. It was just a little tiny lake next to the ice that was ephemeral. It opened and closed and stuff like that. So behind that ramp there, they dug down really far, and they got into what we call the bottom set beds, or lake beds, that were in this lake. And that lake, and those beds show that the sediments, the water drained to the south. So let's look at it to the south. Again, there's the delta up there. And this is, I call the Wilseyville Trough. There's lots of things to show here. So here's where the valley head's ice stopped. Well, that's not exactly true, but this is where it stopped for a long period of time. This gray stuff is a huge plain of gravel and sand called outwash plain. And all this stuff I haven't colored yet. I'm not done with this map. These are kettles and canes. That's where ice stalled and just sort of stagnated and rotted, and all sorts of sediment came down from the hills, and sediment came down here and sort of covered the ice and filled in holes, and it's a long story, but that's how you get these kettles and canes. And this is the Willseyville, I call it the Willseyville Channel. This part of it especially has been known for a long time. I mean, it's really spectacular. It's about 600 feet wide, and right now it's a series of wetlands separated by these yellow globs, which are younger alluvial fans that are fed by streams coming out of the side here. And this is called the Cane Terrace, actually, two of them, one on the other side as well. But this is more than sands and gravels that got fed from up in this area here. So it's a nice story. There's been almost no erosion, so you see the old glacial stuff. Two things. Right here is the watershed now. This is 980 feet. This is the magic thing that led Von Engel especially to say that's what trapped Lake Ithaca, and that's why Lake Ithaca was 980 feet. He kept finding, if you read his book, he finds all sorts of stuff at 980 feet. There, see, I told you, that's Lake Ithaca. And also, the last thing to point out here is all these little dots. Those are cores that I took. And that wasn't easy. This is a real wilderness in there, in small scale. Some of them I had to go in the wintertime on ice, and some of them I canoed into. But anyway, those cores are very interesting. I'm not done with them yet. Oh, one thing first. I'm talking too fast. This is the 980-foot alluvial fan that was supposed to be the drainage from Lake Ithaca. Okay, well, as I said earlier, this is a huge alluvial fan here. That the 980 feet is not, it's something that developed later. The real elevation of this channel that drained Lake Ithaca is somewhere below that. You know, this is all peat and muck and everything else. So we'll look at my coring. This is a section from the very south end all the way up to the delta here. And it's 600 times vertical exaggeration. You can see it's only 25 feet in this direction. It's about, I don't know, 4 or 5 miles in this direction. That's to get it on one page. Okay, this line here is the surface, roughly. It's pretty flat in there. And this is, 977 or something like that. But that's the 980-foot thing. Okay, and these cores, I'll describe them a little bit later, a little more, but I go until I hit cobbles. I mean, I couldn't go any further. They were pretty good sized cobbles, more than an inch or so, to stop the core. So I assume that at least in this area, actually I didn't find cobbles beyond here. In this area, this represented the channel floor. And the elevation is only about 965. So the real, if there was an outlet to Lake Ithaca, it was 965 or so, maybe even lower, because I don't know if I got the deepest part of the channel or not. That's number one. Number two, in this area, I didn't get much in here at all. It's quite thin. This is peat. The reason probably is because the groundwater moving through is oxygenating. It basically just burns away the organic material. It doesn't collect. But in this area, it was deeper and it didn't oxidize. And also, there's a lot of clay in here. And a lot of that clay, where's some, had, let's say, with mollusks, it had these little tiny millimeter scale gastropods and pelecypods. And of course, I run out to PRI and have somebody identify them for me. This area represents a lake, all right, but it was a very shallow lake. It wasn't an open lake like Cayuga is now. It was a shallow lake, almost a pond, weedy pond-like thing. And that pond had an exit or outlet elevation of about 965 feet. Another thing that's interesting, these are some wells. Now I got to do some more coring in here, I'm not done yet. But hard pan to a driller is what we call till. It's basically this real stiff clay with rocks in it. We call it boulder clay sometimes. And that matches what we saw around the delta, that there's till up above this stuff. And we got a date. Where is it? Right here. Okay, this is in carbon years, but this is about 14,000 years old. So that means that there was this ice that came in, that went into the delta, covered the delta, it was younger than 14,000 years ago. I'll get back to that in a minute. Okay, so where do I go next? I'm going to push the button and find out. Pardon me. Oh, yeah. Okay, so how did lake elevation get from the elevation to the top of the delta, which is about 1,010 feet to 1,030 feet? So 1,030 feet there and 1,010 feet here. How did it get from that elevation, because that had to be the lake elevation as well, down to this 950, 965 elevation of that pond I just showed you? Well, this is sort of a somewhat nutty idea, but it's not my outrageous model. The thing that had dammed this small lake in here was ice, basically, the active ice here, and also this rotten ice and stuff in here. And also this elevation right here, the outwash, which is also about 10,020. Well, and this is something that people see quite often now. Sometimes these ice dams break, and you have what's called a glacial lake outburst flood. Yeah, a GLOF. And it's quite possible, I think likely, that the way that the elevation of that lake went from 10,010 to 965 is that a dam burst and water rushed out down here. Okay, the hydrologists have a relationship of channel width, and here's about 600 feet, to meander length, which is about 10,000 feet here, that relates to the flow that caused that. And if you use their calculations, the flow that would have occurred during this GLOF was about 10,000 cubic feet per second. Well, that's not terribly large. That's about the same size as the 100-year flood in 6 Mile Creek now. So it's nothing, no Mississippi or anything like that. So anyway, I think that's how it got there, but that's an aside almost. Okay, the next thing I did is do some mapping. Here's the delta again. Do some mapping in this area here. Let me go back 2 slides. There's one thing I wanted to mention. These contours here, there's a technique or a process called LIDAR now, which is radar done. It's radar run from an airplane. Well, it can be done other ways. That basically is highly computer software analyzed and ends up giving you 2-foot contours. It's utterly fantastic. I mean, it's changed quaternary geology because you can pick out these things that you can never see on the 10-foot contour map. Okay, so onward. Okay, so I'm not showing the LIDAR, but I mapped sort of in this area here. And this area is interesting. These are what we call glacial fluvial sediments, probably deposited when this pond was in existence. The pond was in here. But on top of the glacial fluvial sediments, you can't see it here, but you can almost guess it. There are these sort of arcuate shapes. Those are what we call meander scrolls. And that showed that there was a surface 6 Mile Creek at that time. Just about the same elevation as something we'll talk about in a minute. And I went up this creek here, and there were more of these we call ice contact sediments. Lots of tills mixed in with little bedded sediments, which were probably little puddles and all this kind of stuff. And some of them were all twisted around. It's pretty obvious the ice was going sort of back and forth. The ice was sort of caught in this general area because once it went up this way, up 6 Mile, and down this way, 2 different forks, so it melted faster. But when it got down into this area where there's only one part in 6 Mile, it didn't melt as fast. So it tended to stick in this area here. But it was pretty obvious that it had re-advanced. And what really gave that away is that on the LiDAR it shows really well, and you can actually see it on the ground. That's a moraine. And that's where that ice advanced to. And so this sort of was the first obvious clue that it was an advanced, I don't know, what is this, 3 or 4 kilometers, something like that. It wasn't very far, but there was another little ice advance that occurred. And so let's talk a little bit more about that thing. Okay, this looks like totally something different, but this is just such a fantastic thing that I had to put it on. This is LiDAR also, but this is what they call hill shade, and they crank it through the computer even more, and it's like the sun is coming from the west, and it brings out things that you can't even see sometimes with the 2-foot contours. Using 2-foot contour stuff together with the hill shade is really, really powerful. Okay, where are we? Ithaca College is right there. There's the big reservoir, 6 Mile Creek. There's Inlet Valley, Cayuga Lakes right up there. But the first thing I want to show you, Brian loved this, or maybe you've got this already. Look at these, I call them arrowhead-shaped hills, and how they're sort of sculptured. Well, this is they're actually covered with till, and obviously this is the ice from probably, I don't know how many times, but definitely Wisconsin, late Wisconsin ice, sculpting these things. And these guys here, they're more subtle. They're called mega flutes. And there's some more small ones. But anyway, they really show the direction of the ice movement quite vividly. But the reason I put this on here is this guy here. This is a moraine. And this is the highest of the moraines that Tar found, or that is found, related to this retreat. We'll talk about it later, but there's another one. So where is it? Well, there's part of it here, goes around here. There's a whole bunch of them north of Ithaca as well. But this moraine you can follow really well around here. There's a little bit of it here, and then it sort of gets lost there. It's great. You can never see that now because there's too many houses and trees in it. But Tar could see it, and there's Tar's map, his final map, and there's that moraine. Okay.
He was amazing.
Pardon?
He was an amazing guy.
Oh, and how? Okay, and so now we look at, there's my map, and so I just took there's the moraine that was on the other 2 maps. But I found this. Okay, I looked at the topo map, and here's this crazy creek. It comes down the hill, and then it goes sideways along the side of the hill, and then goes down again. Normal creeks don't do that. And so, I learned by that time, that's probably a moraine deposit. And so I went up there, and sure enough, there's a really nice moraine with a creek left, there's almost no water in it, all caught behind it. But then, all of a sudden, there's this deep gorge, a little gully that goes down here, and these red dots are bedrock, cuts right down the hill here. And these ice margin channels occur this is just one, there's a whole bunch of them up upper 6 Mile Creek and down in Wilseyville as well. They've been written about and everything, but they almost all of them seem to have this common characteristic of being caught behind moraines and then just ending and then a gully goes shooting downhill. Okay, I didn't discover this, but this is known as a subglacial okay, get the damn name now. Subglacial chute. Let's see. And what it represents is that water was going behind this moraine. The moraine is made of clay and rocks and everything. It's impermeable. And then, because the moraines aren't well developed everywhere, they're intermittent. In the place it'll break through and go shooting down under the ice. And going down. Okay, because we know now, and these guys didn't know a long time ago, that there's a whole world of water at the bottom of the ice. There's lakes under the ice in places, there's streams, there's whole hydrologic systems under the ice. And everybody who's worked on this system agrees that this is what they call a wet bottom glacial system, that there was water underneath the ice. Okay, so that's another little clue coming up. So there's that moraine on the other side, and actually you can find pieces of it around here, and tar carried it all the way over to Fall Creek. So here is sort of the situation. Here's the valley heads to ice front. It's usually only found in the valleys itself, and so you kind of fake it over the tops here. I've actually found pieces of it in here. Okay, and here is this little re-advanced ice front that I just got finished showing you, and you can follow it really nicely over here. You can follow it this way as well. It just hasn't been on this map yet. Okay, just stop for a minute and sort of recapitulate. This happened in about 16.5 or 17,000 years. This is younger than 14, maybe 13.5 or something like that, about 1,000 years. Cayuga Lake was at its level at about carbon 14 time at 11.2. So that translates into about 13.5 or something like that. So anyway, the point is that the time difference from this ice, from the valley heads advance to when the ice is totally gone out here, probably way up in here somewhere, 2/3 of it's been taken up in what I've talked about already. You only have about 1,000 years or so, less than that, yeah, about 1,000 years, we'll say, left to get from the ice to get from here all the way up. You know, the ice is well beyond Cayuga Lake. It's well up into Ontario Basin by this time. So, pardon the expression, but all hell has to break loose in that short period of time. I mean, things really have to happen in a hurry. Something kind of weird. Okay. When I showed you this map before, maybe you wondered why I didn't mention these guys here, but I will now. These are channels again, ice margin channels. This one's really neat. There's a moraine this side. This one's easy to explain. It brought water from upper 6 Mile around the edge of the ice down into the Kettle Cane terrain. Brought a whole lot of sediment down into this area as well. This one's easy to, these two are easy to explain. They're alluvial channels. They're streams that fed the delta. They're sort of, you can see this really neat driving along White Church Road. But it's all softened now because it was overrun by that last ice and sort of smoothed off. This is a weird thing. Maybe, I won't explain. I think I have an idea for it. But then there's this guy here. There are gullies. I've walked down these things. They're significant gullies. And you don't know where they go because this has all been quarried out. They're kind of weird looking. I didn't know whether it went down into the Kettle Cane terrain or what it did because the elevation here is lower than the top of the delta. Okay, but I thought things were pretty well solved, except Todd and I got into a discussion, argument one day about, I don't know if you can see the contours of here, but there's this sort of cut through the delta, declivity or whatever you want to call it. And it just goes right across the thing. It doesn't make any sense geologically because the water was coming this way. What would make a cut go through here? And I thought, well, okay, it's railroad because there's one of the Lehigh Railroad went across it and right through there. I thought it's a railroad cut. These guys, cut it. And I didn't know what to do. So actually, I think when I called you, I started saying, well, the railroad buffs, people that know the railroad system here ought to know something about it. So I started calling people. And they said, well, I don't know, but you call this guy. And I didn't know you call this guy. And a Eureka Moment. I was sitting at my desk and I thought, hey, well, let me show you. This is the older map. And it shows the railroad. There's the delta. There's the cut through it. There was this huge, humongous trestle that went through here. And then the railroad went down this direction. But anyway, I thought, well, even that other map, that was contours in 1940, there were aerial photos that were flown in 1936, and I bet you they might have the answer. And I said to myself, hey, you idiot, they're sitting 5 feet behind you in your file cabinet. So I whipped around and pulled it open, and I looked at that photo, and I thought, oh my God, I can't believe this. So, there's one of the photos. The whole series, I'm sorry, look at them in stereo, and let's look at this one first. Here's a LiDAR map of the same area. There's that upper channel. There's the 2 alluvial channels. There's the railroad. Here's this funny, weird channel coming through here. This yellowish area is everything's been mined out. Okay, why did I gasp? Well, look what happened. This channel is the same channel, goes right across the delta. This thing goes 180 degrees on here. You can see that really well in the stereo, but there's a railroad cut right here, which sort of shows you that there's a slope right in here. Okay, this is about 1,050 feet up here. This is about 960 feet. Can't tell because it's so long, but it's 950, 960 feet here. So it really drained. This has to be drained in this direction. What is going on? Okay, this is not a typical stream. I mean, typical. This is the way the water should be flowing down south, but it isn't. It's going this way, right into this high-standing delta. I mean, this delta top is over 1,000 feet in elevation. It's not as high as up here, but it's higher than it was here, and so somehow it had to get through that delta. It's younger than a delta. It cut a hole in it. It has to be something to do with glaciers. All right. Well, this is sort of roughly where I was guessing the front of that glacial re-advance was, right through here. And so, it's logical to say that this thing is related to that glacial front. This is probably, they're probably one after the other. These probably channels that came down along the edge of the ice, and this is something that people see all the time. These channels sometimes go inside the ice, called end glacial, then pop back out again, then go back in, and that's probably why you don't see it here. It's sort of inside the ice, outside of it, or at the edge of the ice. And then, how to explain this? Well, probably when it started, it was on top or inside the edge of the ice at an elevation above 10,010. So it was sort of on top of the ice. And I've seen pictures of these things in Greenland, these beautiful rivers right on top of the ice, big channels. And then it probably cut its way down in these holes called moulins and dropped down to the base. Maybe it started back in this area. Anyway, it basically cut its way down through the ice. That's how to explain the local geometry. But the worst thing about it is what and how does the stream is flowing into the ice. Okay, water flows downhill, or to be more scientific about it, it flows down hydraulic gradients. How does the stream flow into an ice front and go down a hydraulic gradient? Where does it come out? It's got to come out at an elevation lower than it went in. So how are you going to do that? So I thought about it for a while, and here's my solution. Okay, changing scales here. So here we are. That's what we were just talking about. There's Cayuga Lake, Lake Oneida, Little Falls in the Mohawk Valley here, and a little bit of Lake Ontario here. Okay, so this is the outrageous part now. What I'm claiming is that the water flowed down underground through here, through Cayuga Lake, out into this lowland here. That's really not a problem. And came out in this area here. Okay, I missed one thing. All this bluish area is ice at the time. So this is the ice front at the time. We have the ice front fairly well controlled here. I already showed you that. This is fake here. I just sort of, that's logical. But this area has been very well studied. A guy named Jack Ridge from Cross has got VARs, he's got carbon-14 dates, he's got paleomagnetic declination data, so there's no doubt that this was the shape of the ice front at that time, just about 12 to 13,000 years ago in this area. What's the elevation here now? Less than 400 feet. The elevation then was probably at least several hundred feet lower because there's been several hundred feet of differential glacial recap in these areas here. So there's where it came out. That's what I say anyway. There's no problem getting it down 6 Mile, and Hank Mullins and other people think, and I agree, that there was water under the ice in Lake Cayuga at that time, either a subglacial lake or channels. There's something called the Montezuma channels in here, which he used to bring water this way at a younger date, but they're really deep bedrock channels that probably were used a number of times. And in this area here, what we call the Syracuse channels, a guy named Sissons in the 60s said that these weren't just ice margin, these were under the ice to some degree. He said that. He also showed that there were these subglacial chutes coming out of it, which meant that there was drainage even further down into the ice. He also said these things were so big that they were probably used a number of times. See, so, I mean, you have to be real careful. So anyway, this is the, okay, this isn't just outrageous, but it would be preposterous to think that water bored into the ice here and bored a channel through here, all the way down here, and that was it. That's not the way it happened at all. Undoubtedly, there were whole bunches, many of these valleys had drainages at that time. Todd Miller, again, mapped in this area here, in the Dryden area, and he found that post-glacial ice advance as well. And he also came to the conclusion that, hey, there's no lake in front of this thing, and I don't know what to do with the water. It must have flowed into the ice. But he was a coward. He just said it flowed into the ice and came out somewhere at a lower elevation. So, and I suspect, I'm going to be working on it next year, that in inlet channel as well, you're going to find that. And it's still, though, I'm sure, I mean, logic says that this drainage didn't begin at the upper end, it began at the lower end. And quite likely, it actually was related to drainage all the way from Lake Ontario. I mean, the reason I'm saying this, and it's not necessary for the model, but the Canadian geologists are starting to find more and more of these subglacial lakes and subglacial drainage patterns. There could have easily been the entire Great Lakes draining down through here for a period of time. It would happen before, and it happened after that as well. It's not crazy. The entire Great Lakes was draining through that slot right there. Okay, let's see. There's another thing. What else I want to say about this? Okay, this crazy model explains a number of things that I noticed in this area. This is that lower 6 Mile, and I said that the top of the till had no kettles and cames. It was just smooth. Well, that, in my model, that's because the water was going under the ice. Tremendous amounts of water and sediment. They didn't make any kettles and cames because, the ice was above it. The ice was fairly clean because there really, there's nothing above the ice to drop dirt into the ice from up in this area here. Just little bits of hills, which aren't very much around here. I'm wondering, I'll just leave it at the word wonder, whether or not some of the post-glacial gorges were cut during this time, because there must have been an incredibly rapid flow of water and glacial retreat at this time. Again, because I told you how much stuff had to happen in a short period of time. Okay, but one thing I haven't explained yet are those crazy sediments down by Van Addis Dam, that bunch of lake sediments that started with little fine-grained stuff. I mean, the way you get a sequence like that is you dam up something and flood a valley. And that's what happened with Vic's Bars. The ice advancing during the mid-Wisconsin flooded, as soon as one of those drainage divides closed off up above, it flooded the whole valley very rapidly, and that's how you get fine-grained sediments at the bottom. So I'm sort of suggesting that's how you explain that sediment down here, but how did you create this dam, so to speak? Okay, well, when you get subglacial channels, esker-type channels or tunnel valleys and that kind of stuff like this, it means that the ice is not moving to any degree, because if the ice is moving, it's plastic, and it doesn't allow these channels to stay open. It clanks them or squeezes them shut. And so, it sort of suggests or implies that during this period, if this channel did exist, the ice was not moving internally very much at all in this area. But I also said that there's a whole bunch of moraines up the lake here, very well mapped. Those moraines are either recessional or they show periods of slight re-advance. And people know that there were minor re-advances. The ice didn't just retreat monotonically all the way back. Okay, well, either way, whether you had recessional moraines, that means that the front stayed in that place for a while, or it actually re-advanced, the ice had to get active again back in here. It had to be plastic, and it probably closed that channel up. When that channel closed up, what happened? This part had to flood, and so the final part of the story. Oh no! The final part of the story, if it comes back, where's Ingrid? Okay, let me go to the very end. It's pretty obvious to you what happened now. Okay, the southern end of Cayuga flooded again, and went up to this 800, 780, 800 foot level, but then the ice was still retreating. That's all right, it's enough.
Okay.
The ice was still retreating, and that lake level dropped really quite rapidly to down to where it is today. And it didn't drop any further than that because it's trapped at the northern end. I'll leave it there and sort of try to find something to hide behind and catch your flack. So thank you.
Time for maybe one or two questions, and then we're having a reception here to celebrate the groundbreaking of our lodge renovations, and you're all welcome to stay, and Dan will be staying so you can ask him some more questions then.
I can almost guess some of the questions. You could ask you some of the questions. Yeah.
So what's is there a climate blip to explain this re-advance, or is there a global climate blip that
it's
correlates?
There's a bunch of interstates, like Mackenzie Interstate and Younger. The trouble is that, like the Younger Dryas, that's very well expressed in Europe, but it isn't very well expressed here. In other words, I guess what I'm trying to say is it's really difficult to take that was the ice core data from Greenland, and couple it on a real fine scale of what's going on here.
So there isn't an obvious...
It's not obvious. That Valley Head's moraine front is not obvious. Yeah.
You expect something similar up there, the Pisco Inlet and Owasco Inlet and Skinny Atlas at the bottom of those three lakes?
Maybe. Let me just say something. I'm saying a lot of things, but I thought people were going to say, what about Coy Glen and all this kind of stuff? Well, what I'm saying is that many, many interpretations around here have been model-based. In other words, you assume that model that we had, and when you see something like a mass of sediment, you say, oh, that must be a delta. But in a lot of cases, they're not deltas, they're fans. And look and you shall find, or you shall seek in a way. And people just have not been digging these holes. And very few people are involved in this game anymore. There's no money in it. Right? I can explain Coy Glen too, but not here.
In Greenland, do you see these river streams being hundreds of kilometers long?
I've never been to that part of Greenland, but the answer is yeah. There's one that they just was on public media, a huge subglacial valley up at the north end, and they suspect that it's actually draining water. And we had one of our students, she's one of the best sort of glacial hydrologists now working in Greenland, and they're finding these rivers on glaciers that go down these holes called moulins and just disappear. It's really hard to follow these things. I mean, the answer is probably yes, but once the water goes down into the glacier on a scale of, we see at Greenland, it's a little hard to track it. I mean, what they do for Switzerland in these little tiny glaciers is they'll dump a dye down these holes and watch where it comes out, and they'll measure timing and that kind of stuff. You can't do that at Greenland. I don't think. Okay, so anyway, I'll be off in the corner if people want to